good day everybody. So in the analysis of trusses from statics of rigid bodies, we have solved further the bar forces of truss members via method of joints and method of sections. So the video links for these methods will be posted in the description below. Anyway, as for these methods, method of joints and method of sections, these are methods adequate for solving for statically determinate trusses. But what is a statically determinate truss in the first place? So when we say statically determinate truss, we can actually determine the truss bar members making use of the equations of static equilibrium. So once again, when we say statically determinate trusses, these are trusses that can be solved using the equations of static equilibrium. Okay, so next question, what is static equilibrium? So when we say static, it means that it is not moving. So once again, when we say static, it is not moving. And in physics or in engineering, how can we say that a certain entity is not moving? So we can say that a certain entity will not move or is not moving if the summation of all of the forces is equal to 0. Also, you can say that a certain entity will not rotate or will not twist if the summation of moment is equal to 0. So satisfying these conditions will say that the entity is not moving, meaning that it is under static equilibrium. Okay, so basically these are the equations of static equilibrium. But under the summation of forces, so under summation of forces, we have summation of forces vertical and summation of forces horizontal. Okay, so once again, these are the equations of static equilibrium. Okay, so let us now take this truss here as our example. So in this truss here, how many unknowns are there? So how many values must we solve? So as you can see here that we have 33 members. So you can count manually by pausing this video and counting, but I am sure that there are 33 members in total. So we have 33 members. Well, actually, it is already written here. So meaning there are 33 unknowns in these truss members. So another thing, aside from these members, what else should we solve for? Of course, we must also solve for the reactions of the supports or the support reaction. Since we have a hinge here and we have a roller here. So for hinges, as you know that there are two forces acting here, namely horizontal and vertical components. Well, actually, just so you know, there is only one reaction here. If you just know, so it may either be like this or it may either be like this. And since this is a vector, we can actually get its component, which are vertical and horizontal. So in other words, for a hinge support, we can get its horizontal and vertical component, or we have two. So we have two reactions here. And for the roller support, as you know, for roller supports, you only have one, which is perpendicular to the surface. And in this case, this is just vertical. So once again, how many unknowns are there? So we have 33 members in total, and we have 3 support reactions in total. So meaning that we have 36 or 33 plus 3. So that is now equal to 36 unknowns. So you have 36 unknowns. And according to algebra or basic algebra, in order for you to have 36, in order for you to solve for 36 values, you must at least have 36 equations. Okay, so once again, via basic algebra, in order for you to solve for 36 unknowns, you must have 36 equations also. Okay, but how many? How many equations can we formulate from this truss? So making use of method of joints in this one here. So as a review, if you would be getting this joint here, so how many equations can you use? So for method of joints, so suppose that you are getting the bar forces at this joint, you can actually make use of the summation forces horizontal and summation forces vertical equations or equations of static equilibrium. So you can make use of these two. So anyway, so if we have two equations that we can use, meaning that for every joint, we can formulate two equations each. So once again, for every joint, we can formulate for two equations each. Okay, so accounting for the number of joints here, and actually I have already predetermined it. So we have 18 joints in total. So meaning if we have 18 joints in total and we can formulate two equations each, meaning that we can formulate 18 times 2, meaning that we can also formulate 36 equations each. Since we have 36 unknowns and we also have 36 equations, and when we can formulate 36 equations, we can say that this truss here is a statically determinate truss. Okay, so converting that logic into a mathematical equation, that is where this equation came from. So the bar members, or M, plus support reaction must be equal to twice the joint. So meaning, so for member that is equal to, so we have 33 members, plus how many reactions are there? 3. So that must be equal to twice the number of joints of 18. So with that being said, 36 is now equal to 36. So if it is equal, meaning it is statically determinate. So suppose that you have a certain truss wherein, let's say, the bar forces or the bar members are, let's say, 14. So let's say that we have bar members, 14 bar members. And also, let's say that we have 4, let's say, reactions. And let's say that for the number of joints, let's say that we only have 6 joints, just for pretend. And since 18 is greater than 6, meaning that this is now statically, so statically indeterminate. Okay, but for our video, or for today's video, we would be focusing on statically determinate trusses. Once again, when we say statically determinate trusses, we can make use of the equations of equilibrium in solving for our truss members. Okay, so these are the different types of statically determinate trusses. So we have here our simple truss, we have our compound truss, and we also have our complex truss. Okay, so there are special types of statically determinate trusses which are much more complicated than that of a simple truss. So in our previous examples in statics of rigid bodies, almost all of those are simple trusses. So what is a simple truss? When we say simple truss, it means that these are trusses with members set up in a triangular manner. So once again, these are trusses with members set up in a triangular manner. So in this case, we have these members here. So this triangle here, followed by this triangle here, then this triangle here, and this triangle here. And as per the name itself, it is just a simple one. Okay, so for the compound trusses, or for compound trusses, these are trusses with two simple trusses joined together. So as you can see here, we have this simple truss here. Then you also have another simple truss here. And as you can see that they are just joined together by this member, or this bar, and this joint. Okay, so that is for a compound truss. And as for this one below, let's say that this is now a simple truss, and this here is a simple truss. They are now joined together by this member here and this joint here. Okay, so what about for a complex truss? So for a complex truss, it is neither a simple one or a compound one. Okay, so complex trusses often consists of overlapping members. So when you say overlapping members, so suppose that we have this complex truss here, we have this member here, and this member here, though visually speaking, it looks like that they have met at this point, that they have intersected, but the truth is, they did not really intersect. They are overlapping in nature. So when you say overlapping, they may seem that they have intersected, but they did not really meet. So overlapping siguro in Filipino, etong part na to siguro nakapatong dito pero hindi po sila magkadikit. Okay, so for our sample problem, let us have this truss right here. So in this truss, we have a 30 kilonewton load at the left and a 50 kilonewton load at the bottom. So the first thing that we must do is for us to check its determinacy. So let us check if it is statically determinate in order for us to know what method we will be using. So for its determinacy, let us count the number of members. So we have 1, 2, 3, 4, 5, 6, 7, 8, what else? 9, and 10. So, oh, by the way, 9, 10, and 11. So I forgot to count this one here. So we have, once again, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So we have 11 members in total. So 11 members. So how many reactions do we have here? So we have a hinge here, a hinge here, and we have a roller here. So as you know that for a hinge, we have two reactions there. So two orthogonal reactions here. And as for the roller, we have one reaction here. So a total of 3 reactions. So since we have 11 members and 3 reactions, so meaning that we will be solving for 14. So 11 plus 3, that is 14. So we will be solving for 14 unknowns. And with that, we must have at least 14 equations that we should use. So in order for us to know the number of equations that we can use, we must now count for the number of joints in this particular figure. So in order for us to count, so, well, actually elementary. So that is quite elementary. So that is 1, 2, 3, 4, 5, 6, and 7. So 7 joints all in all. So from that, so for these 7 joints, how many equations can we derive for every joint? So according to method of joints a while ago, so like what I have discussed a while ago, so for every joint, you will be having summation of forces vertical and summation of forces horizontal. So meaning that for every joint, you will have two equations of static equilibrium. So with that, meaning that we will once again have two equations per joint. So just multiply this by 2. So for that, we have 14 unknowns. And then we have 7 times 2 equations and 14 equations. So with this being said, if this is equal, then meaning that our truss is statically determinate. So statically determinate. So in an equation form that we have derived earlier, so m plus r, then we will be comparing it with 2j. So m plus r, that is 11 plus 3. And then 2 joints. So we have twice the joints, I should say. So since 14 is now equal to 14, then meaning that our problem here, so our truss here is statically determinate. Okay, so the next thing, so let us now proceed to this slide here. So the next thing that we will do, since our truss is statically determinate, is for us to solve for what we can solve for right now. So as for this moment, we can actually solve for the reactions already, since we only have a hinge here and a roller here. So let me just draw. So for a moment, let me just draw our loads here. Okay, since we have a hinge on the left side, so we have this hinge. So for hinges, we have two reactions. So we have a vertical and the horizontal one. So I will assume it like this. And for the right side, since we have a roller here, it means that we only have a vertical reaction here. Okay, so let us now solve for these reactions. So for these reactions, um, for me, so what I want to do right now is for me to get the summation of forces horizontal, and I will equate it to 0. So this is now our equation of static equilibrium. So what are the horizontal forces here? So we have 30 kilonewtons here, and we also have the horizontal reaction of A. So let us name this as AH. Let us name this as AV. And I will name this as RC, or reaction at C. Okay, so with that, so we have 30 kilonewtons, and since it is pointing towards the right, so positive 30 kilonewtons. And what else? So we also have AH. So for AH, it is also pointing to the right. So I assume that way. So if you would be assuming the other way, so if you would be assuming it like this, so your answer, the value of your A should be negative. But for the moment, since I have assumed it like this towards the right, so I will now I will now add AH here. So this is just an assumption. If ever that your assumption is incorrect, your answer would just be negative. Okay, so with that, AH, so this is now equal to 0. Then solving for AH, so transposing 30 to the other side, AH is now equal to negative 30 kilonewtons. So this negative value here indicates that you have assumed the wrong direction. So wrong assumed direction. So with that, once again, my direction here is incorrect. Rather, this should be to the left. So let me just edit my arrow here. So AH should be towards the left. So this should be the horizontal reaction for A. So A, then H. So that is for this particular value. Okay, so next, let me just get the moment about, so maybe I want to get the moment about this location. So summation of moment about A. So this should be equal to 0. So I will assume a direction. So I will assume clockwise positive. So from that, I will now check all of the forces and and what it would do to point A. So for 50 kilonewton, for this 50 kilonewton load here, if this is now our point A, the tendency of this 50 kilonewton load is for it to rotate point A in a clockwise direction. So if it is clockwise, as you can see, then our answer here should be positive. Or for the moment due to 50 kilonewton load should be positive. So with that, 50 kilonewtons. So this is just the force. So in order for us to write its moment, we must multiply it by its lever arm. So we have a 2-meter lever arm here. So 50 kilonewtons times 2 meters. Okay, so that is for the 50 kilonewton load. So what about for the 30 kilonewton load? Okay, so the tendency of this 30 kilonewton load is to rotate point A in a clockwise direction also. So if this is now point A and this is now the 30 kilonewton load, that its tendency is to rotate point A in a clockwise direction. So with that, this is also positive. So plus 30 kilonewtons times the lever arm. So what is the lever arm? Coincidentally, it is also 2 meters. So the distance from this point up until this point is 2 meters. Sorry. So 2 meters. So what else? So what other forces are present in this figure? So we also have RC, or the reaction at C. So for the reaction at C, as you can see, no pun intended, that the tendency of RC is to rotate point A in a counterclockwise direction. So it will be going here. So with that, since it is counterclockwise, it is contrary to my clockwise positive, meaning that it should be negative. So negative RC times, of course, the lever arm, and our lever arm right now should be measured from this point up until this point. In other words, 2 meters plus 2 meters, and that is 4 meters. So this is now equal to 0. So solving for RC, this is now equal to, so I will now, let's say, transpose this to the other side. So this is now equal to negative 50 times 2 minus 30 times 2. And since we have 4 meters here, so divided by 4 meters, but I'm sorry. Since we have a negative value here and 4, so this is, this should be divided by negative 4. So basic algebra. I'm sorry for stuttering. So RC is now equal to, looking at the calculator to your left, so negative 50 times 2 minus 30 times 2 divided by negative 4. So our answer here is now equal to 40 kilonewtons. Okay, so with that, we already have the value for RC. So we have the value of RC and AH already. So what about for AV? So I think it is better if we would just get the summation of forces vertical equal to 0 and upwards positive. Though you can still make use of this equation or the summation of moment about a certain point. So maybe you want to get the moment about this point. So if you would be doing that, we should still arrive at the same answer. But for the moment, I will be making use of summation forces vertical because I think it would be a lot easier. So summation of forces vertical. So what are the vertical forces acting here? So we have AV, we have 50 kilonewtons, and RC. So I have assumed RC to be vertically upwards. Well, actually, it is really vertically upwards, which is 40 kilonewtons upwards. And I have written here AV to be upwards also. So, okay, so from that, since AV is upwards, so positive AV, then 50 kilonewtons is downwards, so negative 50 kilonewtons. Then RC is also upwards, so plus RC. So this is now equal to 0. And since RC is equal to 40 kilonewtons, AV minus 50 plus 40, this is now equal to 0. So with that, AV is now equal to, so transposing negative 50 and 40 to the other side. So this is now equal to positive 50 minus 40. And with that, we already have the value of AV equal to 10 kilonewtons.